Okay, so in this video we're going to look at types of collisions with a view to looking at momentum. So we start off with looking at elastic collisions. Now elastic collisions are great because essentially what we've got here is we've got two objects that come together, and what you'd expect is them, because it's elastic as the word is after, what you'd expect is that you'd expect the balls to bounce away like so, okay? And that's an elastic collision. So an elastic collision in principle is where what you get out is always what you put in every case. Now what I mean by that is an elastic collision, you get conserved momentum and conserved kinetic energy. Okay, so those are the fundamentals of an elastic collision, and we're going to look at some examples later on in this video, but let's have a look at an inelastic collision. So an inelastic collision is one that does something slightly different. So if you have two balls that come together, so this time I'll draw it slightly different. I've just got one ball that's moving. What ends up happening is that you not there. What ends up happening is that you when the ball travels and interacts with this one, what happens is that they then join together as one kind of big ball and travel on together as a joined up object. So this is inelastic. Okay, now important differences about an inelastic collision: momentum is still conserved, so momentum is conserved, but this case kinetic energy is not conserved. So kinetic energy is not conserved, and that's very important that you remember that in this case momentum is conserved but kinetic energy is not conserved in this case, and we'll do some calculations to show you why that is the case very shortly. Okay, in this next section, we're going to look at just a very simplistic situation of an elastic collision, just to show you how some of the numbers work with some of the calculations you would do. So in the scenario I gave earlier, you've got two balls coming together, but this time I'm going to apply numbers. We're going to say that's 1 kilogram, and that's 1 kilogram as well. And they're both travelling at 1 meters per second. 1 meters per second. So we can do some calculations around this to show what happens. Now, when they rebound, they would travel away from each other with the same 1 meters per second. Okay, there we go. Same 1 meters per second, and they're still 1 kilogram. So that's the situation we're going to deal with. Very, very simple, very easy to get your head around with numbers especially. So first of all, let's look at the momentum before and after. So I'm just going to rub a little bit out just so I can talk about momentum before and after. Now, the way we calculate momentum is we work it out and we represent it by a symbol rho. And rho is equal to m times v, which is the mass times the velocity. So that is the momentum of an object, is the mass times the velocity, and that's a very important equation for your notes. Also it is in the data sheet, so you shouldn't have too much trouble with that one. Now, momentum is a vector quantity, which means something very interesting. So for ball number 1, so that's ball number 1, and this is ball number 2. For ball number 1, we're going to assign that as the positive direction. So because it's 1 times 1, that means it has a momentum of 1 kilogram meters per second to minus 1. So that's what the momentum is there, and you'd expect that to be the same magnitude, 1 kilogram meters per second to the minus 1. So we'd expect both of those to be the same. So that might look okay, but unfortunately, because this is a vector quantity, we do have to assign a direction. So this is positive. So if that direction is positive, then that direction must be negative. And so as a result, that must be a negative 1. So what's my total momentum then of this situation before? Well, it's equal to 0 because plus 1 minus 1 is 0. So total momentum is 0 kilogram meters per second to the minus 1 of this situation. So we've realised that the total momentum of the situation is 0 before the action. So, what can we do now? Well, if we look at it after the situation, so when they're travelling back away from each other, as you will remember, they're both travelling at 1 meters per second to minus 1, 1 meters per second, minus 1. Then we'd expect the same momentum. However, this ball here, is now travelling in the negative direction. And this ball is travelling in the positive direction. So as a result, what we've now got, if we do the momentum for each, we still got, on this side, we've got a positive 1 kilogram meters per second to the minus 1. And on this side, we have a negative 1 kilogram meters per second to the minus 1. All right, and so as a result, my total momentum again, if I look, I've got minus 1 there, plus 1 there. So if I add them together, I obviously get 0 kilogram meters per second. And as you will see, we had that before, we had that there, so we had 0 there. And so now we've got 0 here as well. And that is essentially showing you that momentum is conserved. What I had before is what I have after, and that is always the case with momentum and both elastic and inelastic collisions. So now if we look at the same situation in terms of kinetic energy, so same thing, 1 meters per second, 1 meters per second, 1 kilogram, 1 kilogram. Well, kinetic energy is worked out as a half mv squared. So half mv squared equals kinetic energy. Now, kinetic energy is slightly different because kinetic energy is a scalar quantity. So let's look at the total kinetic energy before. Well, half mv squared. Because we're dealing with nice easy numbers here, so that's 0.5 times by 1 times 1, which is 1. So we end up with a total kinetic energy of 0.5 for the ball number 1. Ball number 2, we'd accept the exact same. And they're both dual values. And so if we add them together, we get a total of 1 joules. Now, if we look at what happens after the collision, well, as you see from the total numbers, if the first ball is then travelling, I won't go into too much detail because you should get this by now. If this ball is now travelling in that direction, and this ball is now travelling in that direction, then they just have the exact same velocity and the exact same mass, so we'd expect exact same kinetic energies, and so therefore the same total kinetic energy at the end. So what you had at the beginning is what you have at the end. Okay, so now we'll look at an inelastic collision and looking at momentum and kinetic energy. Okay, so in this situation, it's slightly different for an inelastic collision because what we've got, again, as I suggested, we've got a ball coming in and hitting another ball which is stationary, okay, this time, just to make this easy. Again, 1 kilogram each. 1 kilogram. And the first ball, ball number 1, is going to be travelling at a speed of 1 meters per second. So let's do the same kind of ideas that we did with the elastic collision. So first of all, we start with momentum. So if we look at the momentum of this situation, well, 1 times 1 is 1, so rho will be equal to 1. So that is our total momentum, because this ball number 2, has no momentum, it's not moving. So it's got 0 momentum, so its momentum is 0, so total momentum equals plus 1. So we've got a total momentum of plus 1 when we add that together, kilogram meters per second. So that's our total momentum there. Just rub that out and I'll put that at the top just to remind you of what's going on. So we've got a total momentum in before, so before equals 1 kilogram meters per second. So let's look at the after then. So after the collision, what we've got is obviously the two balls joined together and travelling at a speed of 0.5 meters per second. Obviously their combined mass is 2 kilograms because they've joined together. So this is something you can observe experimentally, is that obviously when you smack two things together, they travel, if they stick together, they would travel slower than the one that was travelling into it. And we'll hopefully show you that on a linear air track at some point. Or if you don't get a chance to look at it, see it in class, then you should have a look on YouTube for elastic and inelastic collisions to see that actually happening. So let's look at the momentum after then. Well, momentum after is still mass times velocity. So 2 kilograms times 0.5 is 1 kilogram meters per second. And we're happy. Momentum has been conserved. So as we suggested about an inelastic collision, momentum should be conserved, and it is in this case without too much difficulty. But what happens when we look at kinetic energy now? So kinetic energy of this situation, I'll leave all the numbers there. So the total kinetic energy before, half mv squared. So if we're looking at it from the point of view of half of 1 times 1 squared, so that's 0.5. So before we have 0.5 joules. Okay, it's going to be 0.5 total, quite simply because you've got 1 kilogram that's not moving in the ball too, so it's got no kinetic energy. So my total is going to be 0.5 joules. So after, let's have a look at this after. So if we do a half mv squared of that, so if we do 0.5 squared on our calculators, and then times that by half of 2, which is 1, then we get 0.25. Ooh. So obviously those two balls are travelling together, so that is all the kinetic energy that there is in the system, and as you'll notice that the kinetic energy has dropped. Now that's a big indication that obviously kinetic energy is not conserved in an inelastic collision, okay, and that is a very special case. Momentum always conserved, kinetic energy only conserved in an inelastic collision. So you might be asking yourself where this energy goes now. So where is that 0.25 of energy gone? Well, it's gone into essentially allowing this to join together. It's heat energy that's dissipated as the two objects join together.